All right, our next speaker is Gianluca Gregori. He'll be telling us about cosmic magnetic fields and particle acceleration in the lab.
Okay, thank you for, I would like to thank the organizers for giving me the chance of presenting this work here. And I would like to make an apology because what I'm going to talk about is going to be very different from what you've been hearing so far. And what is high energy for me is extremely low energies for you. And this work starts from a discussion that I had many years ago with people in Oxford, very known cosmologists or astrophysicists like Subisakar or Tony Bell, about doing experiments in a laboratory using plasma physics, a laser-based plasma physics, try to address problems that are important in astrophysics and try to address relevant questions. So the first thing we're going to look at is a discussion we had is why there are magnetic fields in the universe to start with. For example, we know from farther rotation and synchrotron emission that the universe is magnetized everywhere. In cluster galaxies, you see magnetic fields on the order of a few microgauss, and galaxies as well. In filaments, the magnetic field is inferred to be a few nanogauss. And even in the empty space between cluster galaxies, you see magnetic fields on the order of a fraction of femtogauss. The problem is that when you think about the primordial processes that generate magnetic field, the numbers you come about, basically all the models don't get any magnetic fields higher than 10 to the minus 21 Gauss. This number is much smaller than these values which have been observed. So there is probably something else going on, and that something else is related to the fact that when people do structural formation, this results in a web, which is again made of clusters, filaments, and voids. And if we look at the distribution of the gas and at also at the shocks, we see that the entire universe is permeated by shocks. And these shocks are both high Mach number, small Mach number shocks. But what they do, they inject vorticity into the intracluster medium. And because of that, the overall state of the universe is that of a turbulent fluid. If the fluid is turbulent and there is a tiny magnetic field to start with, then what could happen is that the magnetic field is tied into the plasma. And so as the shocks inject vorticity, because they are corrugated or go through galaxies or cluster of galaxies, these shocks, essentially what they do, they twist the magnetic field. And this twisting process can be described from the induction equation, an equation like this one. Essentially what it says, at least in the initial linear phase, the magnetic field grows exponentially. And this exponential growth is what is believed to be the source and amplification of the magnetic field. And people have done numerical simulations trying to explain this process. So this is what we call the turbulent dynamo. Essentially, you have a magnetic field line that you stretch, you twist, and you fold. And the process this process generates the amplification of the magnetic field, and is set at a rate which is given by the eddy turnover time, which is the ratio between the scale at the largest scale divided by the velocity of the fluid. The problem is that when you do numerical simulations for this type of process, what you get is that any numerical simulation, cosmological numerical simulation that you do, achieve typically on the larger scale a very modest magnification of the order of factor of thousands. So going from 10 to the minus 21 Gauss to a microgauss, this factor of 1,000 is not sufficient. So what we came about is, why don't we do some experiments in the laboratory, try to see if we can excite a dynamo and learn something about it. So what we're going to describe are experiments. And these experiments are done in laser laboratories. And the idea is that the equation that describes the evolution of the cosmic plasmas are essentially fluid equations, which are this form. So these equations are scale invariant. So that means that if these equations are valid at some scale L, velocity u, and density u, in the astrophysical case, in the cluster of galaxy, then you can multiply these terms by some suitable constant, and this equation will be applied in the same way, will be valid in the same way in a laboratory scale, which is probably of the order of a few centimeters or even less. And in order for this process to be applicable, what you need is that essentially these dimensionless numbers, which are the Reynolds numbers and the Peclet number and so on, they need to be both large in the astrophysical case and in the microscopic case. So this does not mean that the microphysics is the same here and there. The microphysics is going to be different, and the microphysics is encoded in this dimensionless number. However, if they are large, both in the astrophysical case and in the laboratory case, then the equations will evolve in exactly the same way. And so if this can be achieved, then what you can say is that laboratory experiments can be complementary to astrophysical observations and numerical simulations. First of all, because compared to observations, in experiments you can have a very detailed measurements of all the plasma properties. I can measure exactly which is the temperature, densities, and everything else. Also, experiments can achieve conditions that are difficult to achieve in simulations. For example, we can go much beyond any linear regime. We can have much larger scales, and we can have a much larger number of particles. So far, difficulties are remained in achieving these dimensionless numbers that are large enough for example, for Dynamo to become operative. Again, is a disclaimer here, which the full range of parameters, so I'm not going to get the highest energies or temperatures that have been seen before. Right? These are not going to be the same. And they are not accessible in the experiment because the microphysics is going to be different. Right? So we do these experiments at laser facilities where these lasers work in exactly the same way as this laser. Right? This laser has an energy of probably a fraction of a millijoule. These lasers here, like the Omega laser at the University of Rochester or the National Ignition Facility at Lawrence Livermore National Laboratory, those are lasers that are few, 2 or 3, depends which type of football stadium we are referring to, size. They can deliver energies on the order of a megajoule, right, or hundreds of kilojoules in a nanosecond pulses. Right? The type of power that they deliver is in the order of petawatt. Right? So put on a scale, this corresponds to 2 million nuclear power plants. Right? So the power we can deliver here is exceeding the US national grid. Right? So what we can do now is to create, with these lasers, finite volumes. Right? Not a particle, but a volume of a cubic centimeter, for example, that contains plasmas, which has a temperature of a keV, and a number of particles around 10 to the 20. Right? So we don't have the highest energies, but we have a very large, high energy density. Right? So this is the key point that we are trying to achieve here, is to use this high energy density in order to explore conditions that can be important for astrophysical plasmas. So this description of the experiment is very, I realize it's very complicated for anybody that has not seen this before. And this is an example of a target we use. These targets are made, so the important part, there is a piece of plastic here and a piece of plastic there. And we fire laser beams. So these facilities have on the order of 60 to 100 different laser beams that can be pointed in different directions and so on. So we fire laser beams on this side and that side. So as the laser beam impacts into the target, it vaporizes the target, and then there is ablation pressure that pushes this plasma here from that point towards this direction and towards that direction. So the plasma goes through these grids here that enhances the turbulence and then collide in the center. So in the center, you have a colliding plasma. It becomes turbulent, and what you want to do is to study the property of a plasma, and we do that by looking at the X-ray emission, like you would do with a cluster of galaxy. You look at the self-emission of this plasma, and try to learn something about that. But you can also do something else, like you can fire another laser beams into this plasma and look at the scattered light. You do Thomson scattering. Right? Thomson scattering also delivers very important information about the property of the plasma. Another thing we can do, we can put another little target there. So this is a capsule that contains a few hundred microns capsule that contains deuterium and helium. As you fire beams into this capsule, the capsule compresses, implodes, and generates fusion reactions, DD and D-helium-3 fusion reactions that produce protons. So these are lower energy protons, are 15 MeV and 3 MeV protons that are emitted everywhere. Some of those protons go through this target, and now we can image those protons and again learn about the statistics of the fields in this system. Right. And so what we do first is to do numerical simulations and try to understand what's happening in this system. So these numerical simulations are done in collaboration with the University of Chicago using the flash code. The flash code is one of the most commonly used codes in astrophysics. For example, used to look at supernovae explosions, core collapse supernovae, for example. So it's the same code. The only difference is that this code has been developed with an additional package to include the full laser transport, propagation, and radiation transport, which is important in these experiments. So this is the example, is a 3D simulation of entire experiments. There are the two foils here, the two grids. The laser will come from the top and the bottom. And now what you see is that this foil is exploding and launching the jets on both sides, going through the grids and colliding in the center. Right. So this is what the simulations predicts. And now we are trying to do the experiments and see if we can match the simulations, which is also a good thing, and understand if what we predict is actually happening in the experiment. So as I said before, what we're going to do is use diagnostics that are common in astrophysics as well. So we look at the X-ray emission from the center of this target. And this is what is done by many people that look, for example, at cluster of galaxies. They have an X-ray map. They look at the fluctuations of the X-ray intensity. And from the fluctuation of the X-ray intensity, they get an information of the turbulence in the system. So the same people are collaborating, those same people are collaborating with us to do this type of analysis. Right? As I said before, we look at the protons that are generated by these capsule implosions. The protons go through the plasma, and they are deflected by the fields, these small angle deflections. And by looking at the deflections, we can have an information about the topology of the field. The third diagnostics, as mentioned before, is Thomson scattering. Thomson scattering provides a detailed, time-resolved, local measurement of density and temperature in the system. And we can also do further rotation as well, but I will not talk about that here. And so this is the data, experimental data. Here there are the two grids. The plastic foils are here. And now the plasma starts to light up as it collides. Right? And you see here in the collision, the plasma gets hotter, and then you have this modulation in the X-ray emission. Okay. So this is an example of the X-ray data. So these are soft X-rays in the KV range, in the KV band. So there is a modulation in X-ray intensity. So if you assume your plasma is optically thin and is described by the Planck opacity of this type, so now what happens is that what you can say is that the modulation in the X-ray intensity, right, is proportional to the modulation in the density. Right. So essentially, by taking a Fourier transform of this data, what you can do is understand, basically you can measure the spectrum of the density fluctuations. You can have, and these are the data here, the circles corresponds to the spectrum of the density fluctuations in the data, which follows, is not a huge dynamic range, but still follows a minus 5/3 power law, which is what you would have expected from Kolmogorov hydrodynamic turbulence. Now, the squares here corresponds to the data that you get from the flash code, and you can see that the agreement is pretty good. These are density fluctuations, right, in the density. However, what you really want is the velocity fluctuations. It turns out if you are in the subsonic regime, as we are in these experiments, then density fluctuations and velocity fluctuations do exhibit the same spectrum. So now if you assume that you are in the Kolmogorov regime, that means that the velocity follows a relation of this type, which is the classical Kolmogorov relation in the inertial range. So it means that in principle, if you know the velocity at one scale, little l, you can get the velocity at the larger scale by using a relation of this type. And this is what essentially we do by looking at Thomson scattering. So Thomson scattering is scattering of photons of, in this case, ion acoustic waves in the plasma. So for people that is more familiar to solid-state physics, this corresponds to phonons. Right? So essentially, we do the equivalent of scattering of phonons in a solid, but we do that in a plasma. And these two features here This corresponds to the ion acoustic, so the Stokes and the anti-Stokes component of the scattering. And you get very important information from looking at these two features. The central peak here corresponds to the unscattered light of the laser, right, at 5 to 6.5 nanometers. So the first information is that the shift of these peaks compared to the central peak is Doppler. It's a Doppler effect. So by looking at the shift, you can measure the velocity of the plasma before and after the collision. And these are the numbers. About 200 kilometers per second is the velocity that they have when they collide. You can also look at the separation between these two peaks. The separation is a measurement of the, essentially the sound speed, right? So the sound velocity is nothing else but the electron temperature. So you can measure the electron temperature by looking at the separation of these peaks, right? And you can measure the temperature as a function of time, and you see that after the collision, the temperature is about half a keV and stays almost constant all across in the center during the duration of the experiment and the turbulence. Finally, what you can do, the thing you can do is look at the width of these features. The width of these features give you an information on the turbulence, right? Is the turbulent velocity at the scale of the probe, which is 50 microns. And then you can infer from, since you are in inertial range, a velocity at the outer scale, a turbulent velocity at the outer scale. So essentially, we have all the information to characterize this plasma from a microscopic point of view. And now let's see what happens in terms of dynamo. So these are simulations done by my colleague Alex Ceccocini in Oxford, and these are standard MHD simulations of turbulence. You have a box which you steer with some driving force. You put an initial value of the magnetic field, which is this one here, magnetic energy, and you see the evolution of this magnetic energy as a function of the conductivity in the plasma. So it's higher conductivity, which means higher magnetic Reynolds number, and this is more conductivity. So if the conductivity increases, the magnetic field increases up to a point here, this point here. Well, if the conductivity is large enough, then the plasma becomes, achieves the conditions that you want, where the dynamo, the stretching, twisting, and folding of the field lines is sufficient to bring the magnetic field in equipartition or close to equipartition with the fluid kinetic energy. Question, are we in this regime? So as I said before, we can measure velocity, temperature. With Thomson scattering, we can also measure densities. And I didn't talk about that, but it's something can be done as well. So we have all the information here. We can calculate all the numbers, like the Reynolds number, the magnetic Reynolds number, and we are in this regime here. Right. So we are in a regime where if there is dynamo, we should be able to see it. Right. And if there is dynamo, we should reach equipartition between fluid motions and magnetic energy. So now we look at the data from this data from protons, right? So protons go through the plasma. These are for us are high energy protons, 15 MeV. Not that high for you guys, but what happens? The protons go through the plasma, and now they experience small angle deflections, right? So this was done at a time where the two fluids, two jets didn't collide, and you see a smooth distribution of the protons. They arrived at the detector. In this case is a CR39 nuclear track detector plate. And in this case here, a few nanoseconds later, what you see is a formation of caustics in the image of the protons. These caustics are essentially due to the fact that the protons are deflected by a field, a path-integrated field across the plasma. So now, if these deflections are not large enough, what we can do and if there is a one-to-one relations, what we can do is invert this map, right, and retrieve which was the initial path-integrated magnetic field that was the source of these deflections. And with that, provide a measurement of the magnetic field in the plasma. So we can do this inversion, and what we see is that initially, the magnetic field is smaller. So we talk about RMS field, which is of the order of a few kilogauss or smaller. But then, as the plasma collide, the magnetic field becomes much larger. You see the formation of all these filaments. And essentially, what you have is an RMS field which is much larger, on the order of 100 kilogauss, and a peak field which is much larger, which indicates amplification of a factor of 20. And with these values of field, you are in near equipartition with the kinetic energy. So is this process correct? So a way to verify it is assume that this is our initial field in the plasma, done with the 15 MeV proton images. And now calculate which would be the field that we expect to get if there are 3 MeV protons. Right? So now these are the 3.3 MeV protons, and this is the predicted deflections for going through this magnetic field. And these are data. You can see that is very, very similar in both cases. And so this is a cross-check that the analysis is correct. But also what you can see is that in this case, the data looks a bit more diffuse than in this case. And this brings to the second part of the talk, which is actually much shorter than the first one, which is about particle acceleration. So I don't want to talk much about particle acceleration because you've heard a lot about this conference. So the source could be many things like supernovae, AGNs, gamma ray bursts, and so on. And we see very large energies in apparent defiance of thermodynamics. So can we do experiments to learn something about that? And the key point is that the idea of particle accelerations is based essentially through the Fermi process, which in the initial version was you have fast particles that collide with moving clouds, and these particles can gain or lose energy in a collision, but head-on collisions are slightly more probable, and so there's a gain in energy. And this is the second-order Fermi process. First order, it works in a slightly different way, but it's based essentially on the same idea. And these are the sources that we discussed before, AGNs, neutron stars, and so on. But the evolution is the same. In all cases, it's governed by a diffusion equation, right? And in principle, there's nothing that says that astrophysical sources and laboratory plasma can behave in the same way in terms of particle acceleration. The scales are going to be very, very different, but we can also think of particle acceleration experiments done with this type of plasmas, and then use them as a test bed to validate the models that we have. Are they correct? Do they predict the same thing? Or do we get something completely different? So this was an experiment based on the same platform as before. So you have two foils, right? We fire laser beams, they go through the grid, they collide in the center, and we use, again, a capsule, which is made of the deuterium and helium, right? And we implode that, produce protons, but these protons now are collimated with a tiny pinhole, 300 microns pinhole. They go through the plasma, and then, as they pass through, they acquire transverse deflections. They diffuse, right? And we can measure this diffusion. So what we see here is the image of that 300 micron pinhole when there is no plasma in the system. So this is the initial beam size. And what you see here is the same image through a magnetized plasma where Dynamo is operative. There is a turbulent magnetic field. And you see, especially in this case, there is a large diffusion of the initial beam. Right. So now, what is the source of this diffusion is essentially due to the fact that you have a path-integrated field that deflects the particles. Right. These are the deflections done as a function of time, also for different energies and so on. And essentially, what we need to do to calculate this perpendicular velocity, we need to know the structural turbulence, but we do that from what I said before, the first part of the talk. We know the structural turbulence, so we know the scale length, right? So we can do these calculations very accurately. And also we can think of which is the source of the field that produces the deflections. Of course, the first term that you can think of is just Lorentz force. You have a magnetic field, and a particle that goes through and is deflected by the magnetic field. But can also have other terms, additional terms in Ohm's law. And now we'll see which term is important or not important. So the first one is the Lorentz force. This term does not produce any acceleration, only deflections. But these deflections are independent on the proton energy. So if we see deflections that are different at different energies, this term is not the one that we see in the data. There is a term here which produces a field due to magnetic field diffusions. It's a diffusive term. But since we are dealing with a system which has a large magnetic Reynolds number, diffusion is not important here. And so this term is actually very small. So we are left with a term here, and now it's everyone's guess what it could be. It could be subgrid electric field, but it becomes important. So what we thought is the first order correction to Ohm's law, which is a baroclinic thermoelectric field. Essentially, it's due to an electric field which is produced by pressure gradients in the plasma. And scales as T over a scale length. Since this field is going to be largest at the smallest scale, the relevant scale length here is the resistive scale, which we know because we know all the property in the plasma. And if we put the numbers here, we know the temperature, we know the scale length, and for 3 MeV protons, we get a perpendicular deflections, which is actually not so different from what we see in the data. And so if this is the field that produces the deflections, that gives an acceleration of about 100 keV over 3 MeV protons. So it's a few percent effect. And again, this is a starting point, right? We are not having TV energies here, right? It's not high energy cosmic rays, but still it's a process where you can do experiments, you have a model, and you can validate your model with very high precisions. So now I would like to thank, to conclude, all my collaborators, especially the students and postdocs who work with me, also the colleague in Oxford, Tony Bell, Alex Secoshini, Subir Sakar, as well as all the people in Chicago that did a lot of work with us in trying to develop these experiments, have ideas. Their input was very important, in particular Petros Seferakos and Don Lamb. And then all the other collaborators here across Europe, United States, and Japan. And this is the summary. I don't think there is much time left, so you can read the summary here. Thank you for your attention.
We have time for a few questions.
So I have a quick question over here. So in your introduction and motivation, you discussed the fact that it seemed like the dynamo was maybe insufficient to give the amplification, particularly for the intergalactic magnetic fields. And so if the dynamo is really what's going on, would you have expected to see some surprises here? Or do we have any, is there anything from this experiment that allows us to help resolve that part of the puzzle?
Well, the only thing that we can say is that we do get equipartition between kinetic and magnetic energy. Right. So at least in the laboratory, the dynamo works to the expectations that the system equilibrates between the two energies. We have, everything depends on the eddy turnover time. So we have an eddy turnover time of about a few, which is not that different than what you see in galaxy clusters. So that is an indication that things are not that different.
We have another question over here.
So you have a nice X-ray movie from the experiment. I was curious if there was sort of a synthetic X-ray movie from the simulations.
We didn't do that yet.
You compare the Fourier spectra of the simulations and the experiment for the X-ray images. It just makes me worry that the Fourier might look okay, but then if you actually compare them side by side, they might not look as good.
No, we didn't do the synthetic X-ray images. It's a good point. We should do that. Thank you.
We have time for one more question. Anyone else?
Can you say something about the National Emission Facility experiments you might be planning?
Yeah, we actually did already experiments on the National Emission Facility. The main difference is that the laser is much bigger, right? And instead of, so the experiments I described here were done using 20 kilojoules of laser energy. At NIF, we have been using 200 kilojoules to half a megajoule. So now what happens is the velocities becomes much stronger, much higher. So ideally what we expect is to go in a regime where, so the experiments I described is pure MHD. So we would like to go in a regime where we go beyond the MHD approximations, where kinetic effects can become important. And that brings a whole different story in terms of dynamo, because it's a kinetic dynamo, it's not an MHD dynamo anymore.
All right, let's thank Gianluca again.